This is chapter 10 and number 1. Okay, which of the following should have the lowest boiling point? The controlling theory here is boiling point is dependent upon what? It's dependent upon the intermolecular forces. So the one with the weakest intermolecular force among the molecules should be the lowest boiling point. It should take less energy to break those bonds. So that's what we're looking for, right? We have through E. Right, we've got sodium sulfide, we got hydrogen fluoride, got ammonia, and we've got nitrogen and water. Okay. So, what type of forces are we dealing with? Well, we could have ion-ion interactions, right, for ionic compounds, cations and anions. We could have dipole-dipole interactions, which are a little bit weaker. Or we could have, well, we couldn't have ion-dipole because, you know, I guess there are circumstances where we could. All right, so let's just put it up there. We could have ion-dipole. Because if molecules are large enough, they can have an ionic end and a dipolar end. We haven't covered that, so we're not going to hammer that one too hard. And then what's left over? Right, we have London dispersion forces. And this is strongest to weakest. So we want something with the weakest intermolecular force, something here, right? Well, London dispersion forces are always there. It doesn't matter what the molecule is. London dispersions are always there. It's just that they're so weak. If these others are available, if they're also there, they swamp this out, right? You don't even know it's there. You can't measure it. Well, it's not easy to measure it. So if we have any ion-ions or dipole-dipoles, then the London dispersions count little or nothing, right? Sodium sulfide is an ionic compound. All right. HF is polar, right? So it's going to have dipole-dipole interactions. This will have ion-ion interactions. Ammonia, is ammonia a polar molecule? Yeah. Oh, we've drawn that one before. Right. It's got that pyramidal structure, and its dipole is like this. So this one is polar. How about dinitrogen? Right? If we draw dinitrogen, we know that it's like this. Right? It's completely nonpolar. Right? So these don't count. London dispersion forces are the dominant forces for it. So we have nonpolar. And water, of course, is polar. We know that. Right? So this one is subject only to the weakest forces available, London dispersions. It will have the lowest boiling point of all of these. In fact, its boiling point is minus 195 degrees C, right, where water is 100 degrees C. I don't know what the rest of them are. This one's really high. That melting point is extremely high. So the boiling point is going to be even higher. Okay, so we found our answer. Well, if I flip the question around and say which one has the highest boiling point, it will be the one with the ion-ion interaction. Sodium sulfide would be the highest boiling point. And then you have intermediates here, here, here. Okay? All right, so that's number 1. And let's see, scroll for number 3. Here we go. When a water molecule forms a hydrogen bond with another water molecule, which atoms are involved in the interaction? Pictures are very useful. Right? We know this is a water molecule. We know this end is slightly negative, and these ends are slightly positive. Let's balance it there. So if another water molecule approaches, how is it going to approach? Well, it could be any number of ways, but in which way will it approach that forms a bond? You would have to approach with the negative side of the molecule there, right? Like that. And that's how you would form a bond. If it approached with hydrogens this way, they would repel each other. So it'd have to approach, it's a random, it's probability, right? So if it approaches this way, then we form a bond. If it approaches any other way, there's repulsion. Okay, so which one of these statements satisfies? A hydrogen from one molecule and a hydrogen from the other? No, that's repulsion. B, a hydrogen from one molecule and an oxygen from the other. Yep, that's it. C, oxygen, oxygen, oh, you get repulsion there. An oxygen and hydrogen from the same molecule? I don't think so. They're already bonded, right? And the molecule is too small. You can't get them to wrap around and do that. Now, with big molecules, they can wrap around and have polar interactions within the molecule. Right? But we're not interested in that right now. 2 hydrogens from one molecule and 1 hydrogen. Okay, we go from the sublime to the ridiculous. B is the answer. 1 hydrogen from one molecule interacts with the oxygen of another to form that dipole-dipole interaction. All right, that was 3. There's 4. And 4 references, picture number 3. Okay, so they're both on the screen at the same time. That's good. So if we're looking at 3, Roman numeral 3, what are we seeing there? We're seeing a depiction of hydrogen chloride. That. Chlorine is more electronegative than hydrogen, so we're going to get right, a dipole that direction. And that's negative, that's positive. Okay, so when they interact, they're going to interact in such a way that, say, like this, that, this negative. Okay, so which of these statements is or are incorrect concerning the drawing of the 3? So we're looking for the one that's wrong. Electrostatic interactions exist between the molecules. Oh, definitely. Right. They're not complete ions, but they're still electrostatics. They're partial charges. So A is true. About B, the molecules find the best compromise between attraction and repulsion. That's also true, because even though that positive and that negative are attracting, this positive is still out there, right? Even though it's farther away, you still get some repulsion here between these two. So it's going to try to push away, and this bond here connection is going to pull it a little bit, but then this is closer, so you get an attraction there, and it's a balance between the two. Right? The distance between these 2 molecules is determined by the balance of attraction and repulsion. So B is true. These molecules exhibit ionic bonding. Right? Are there any ions there? No, I don't think so. So that was false. Okay. Since E says two of the above statements is incorrect, then we got to go all the way down to D to see if E is valid. OCS exhibits this type of interaction. What is OCS? Oxygen, carbon, sulfur, right, in that order. So what would be their Lewis dot structure? Well, let's see, oxygen, 6 and 6, 6, 6 valence electrons, 4 here, right? So that's 16 electrons, right? 2, 4. We have 12 left over. Let's start from the outside and work our way in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So these have octets. That one has an octet. This one doesn't. So we're going to, for balance, we're going to take that group and make a double bond here. We're going to take this one and make a double bond here. So that would be our Lewis dot structure. Well, is this a polar molecule? That's the question. Okay. Oxygen is more polar than carbon, so it's going like that. Sulfur is more polar than carbon also, so it's going like that. But they might be opposite, but they're not equal. Right? This is a linear molecule, right? We have two groups around the central atom. Right? Two groups is linear, according to the VSEPR model. But this one is a stronger dipole than this one is, because oxygen is above sulfur. And right, remember the trends, vertical trends, increasing electronegativity as we go up like that. So from here to here, oxygen's more polar. So overall, we get polarity like that. So yes, this type of interaction would be exhibited by that molecule. It's unbalanced in its charge distribution. Right? So that means this one is also true. And that means E is false, because there's only one that's wrong in this group of 4. Okay? I'm not hearing from the peanut gallery. I assume you guys are getting all this. Either that or asleep. All right, that was 4. And let's try number 6. Which best explains the following trend? Okay, looks like we've got noble gases. Helium, neon, argon, krypton, xenon. That's far down they go? Yeah. And the boiling points of each one of these in Kelvin is, this should be 4, yes. 25, 95, 125, and 170. This is K, right? So we haven't even gotten to room temperature yet. All right, what explains that? Why do you get this increase here? Well, what changes? As the boiling point increases here, what's changing over here? The molar mass. Molar mass is increasing, right? Molar mass is increasing that way, which means that these atoms are getting bigger, right? And if you have a larger atom, then the valence electrons that surround that atom have more room. They have a lot more room. So what that means in practical terms is that the distribution of electrons around, say, let's take the biggest one, xenon, you can have a distribution here of electrons on that side and a deficiency on this side. and they're further apart, which means they're more likely to be stabilized by that distance. Now, stabilized is a relative term, right? They're stable for maybe a picosecond, right? But you get that distribution is more frequent and more pronounced as you get bigger. Well, what does that do for the boiling point? Well, the longer you can maintain these London dispersion distributions here, the larger the London dispersion forces become, and that reflects itself in the increase in boiling point. Okay, it's simply based upon size. So the explanation for this is London dispersion forces. You don't have dipoles available, you don't have hydrogen bonding available. Le Chatelier was just thrown in there to confuse you. Right? None of these. London dispersion forces explains this phenomenon.
Do you have them muted by accident? Is the microphone over there as a line for it?
I think that's that microphone is the one up here, so that we don't get feedback.
Oh.
Yeah. Each one of the participants has a an unmute. Right. If I unmute this one, let's see, can I do that? I can't do it from here, but if I unmute it over here, let's see if I'm right. It changed. Yeah, it changed.
Okay. Just checking.
Yeah, all microphones are not alike. Let's see. I got one that works. Let's try green. Let's see, that was 6, now 7. Yep, we still got time. What in the world? It only helps a little. Okay, 7. Here we go. Which of the following compounds has the lowest viscosity? Okay, we're still, this discussion is all based upon intermolecular forces. So which one has the lowest viscosity?
Is anyone else's board very blurry? I can't really see you, Dr. Vaughn.
Can't see me? Oh yeah, it did get blurry. Okay, here's the problem. I can't use my Logitech camera control where I can say, this is, what's the term? Autofocus. This thing automatically autofocuses. I can try again. I can try to bring up the camera control.
Oh, it's okay. It looks good now.
Yeah, that's one of the reasons I like to use the Logitech camera app, because it allows me to fix it and not let it autofocus. Autofocus is a real mess. But when I do that, for some reason today, it shuts my picture down. So you can't see me at all. So if I get back here, okay, it looks like it's still focused.
Yep, looks good.
Okay. So I'll try to stay over here and only go over there to change problems. So which ones have the lowest viscosity? The lowest viscosity is going to be the substance that has the weakest intermolecular forces. So if we've got this gas and this, I'm going to use the condensed form here. This is 27 carbons and how many hydrogens? 56 nitrogens. And then water is a liquid. Let's see, this is a liquid also. And then this is a gas. And this is a liquid. Okay. So we've got a mixture, we've got several types, gases and liquids. If I were trying to solve this problem in a test taking setting, I would eliminate, I'm looking for the lowest viscosity. Right? As a general rule, gases are much, much lower viscosity than liquids. Right? So we can do away with that liquid, and that liquid, and focus on these two gases. Right? The lowest viscosity is going to be one of these gases. Well, which one has the weakest forces? Well, this is a polar compound. So you're going to have dipole-dipole interactions. This one we've seen already is nonpolar. So the only possibility here are the London dispersion forces. This will be the lowest viscosity. Okay? If we were to say which one is the highest viscosity, then we'd look at the liquids and eliminate the gases. Then we'd be looking at this one, that one, and this one. That's where it gets tricky, for the reason that this is nonpolar, so it's going to be a lower viscosity than water. We can throw that one out. Then it's going to be a battle between this polar molecule and this nonpolar alkane. Right? That's the organic chemistry term for this one. It's a series of carbons hooked together, and all the rest of the bonds are with hydrogens. Here's the thing. London dispersion forces are always there. This one only has access to London dispersion, but it's a huge molecule. So those distributions of electrons can occur all over it. And with a long molecule like that, they can lay down side by side and have a lot of strong interactions between the molecules. Whereas water is just a little molecule, even though it's polar, it only has polar interactions between this molecule and maybe 3 or 4 others. Right? So as it turns out, the stronger forces in this case are the London dispersion forces for this huge molecule versus the water. So this one has a boiling point of 100 degrees. This one has a boiling point of maybe in the neighborhood of 60 degrees, right? So boiling point, yeah, this one would have a higher boiling point, but viscosity is not just dependent upon that factor. It's dependent upon shear. Can we force molecules past one another? And in this case, it's not just the London dispersion forces, but it's possible entanglement. Right? If you put 2 ropes side by side and pull on one of them, they're just going to pull apart, right? But if you wrap them around and tie a knot, they're gonna hold, right? And that's a similar thing happens with these big molecules. Now, the only reason I brought that up was just to kill another 5 minutes, I guess. But to answer the question, nonpolar nitrogen gas is the least viscous of these. When you're talking about really small molecules, then the available forces they have to attract one another, that's as far as you need to go. When you get into the large molecules where you can have entanglement, then you have another can of worms. Okay, number 8. When a nonpolar liquid displays a convex meniscus, so it displays meniscus like this, rather than convex, which would be water on glass. And reading further into the problem, Yeah, reading further into the problem, the tube is made out of glass. So, which of the following explains that behavior? A, it has a low surface tension, therefore clings to glass. What if it has a low surface tension? Right? Low surface tension means that the forces attracting the molecules together are very weak. Right? So the forces, we're looking at a balance between cohesive, it's a battle actually between cohesive and adhesive forces. Cohesive forces are the ones that are internal to the substance. Adhesive are the ones between the substance and its container. So if the cohesive forces are weak, which is what this implies, low surface tension means weak cohesive, then the adhesive is going to take over, and it's actually, you would expect that type of meniscus rather than this type. So A is false. How about B? The cohesive forces are stronger than the adhesive forces. Yes, that's true. And since E says none of these, we found our answer. Okay. All right. Let's scroll to the next one. Maybe I can get, no, I can only get two. So let me just do those two. 9. Which substance can be described as cations bonded together by mobile electrons? Does that bring back any memories? How about the electron C model for metals? Remember where we had metal atoms? And then we had electrons around them like that, just scattered. And they were kind of like the plum pudding model for the atom. These are cations. And all these electrons can move. So which one satisfies those conditions? Well, it's not going to be krypton, because this doesn't form cations. Right? This is a complete atom, and its electrons are bound tightly to the atom. It's not octasulfur, right? Because that's a molecular compound. Right? It doesn't form cations. It forms a network of 8 sulfurs. Right? Potassium chloride is ions, right? Not free electrons. And HCl is also a molecular compound. Right? So this is polar, this is ionic, this is nonpolar, and this is nonpolar. So the only one that fits that description is silver. You have silver atoms, and the electron C model portrays them as ions surrounded by electrons. Sea of electrons. All right. Now we know that this model is not accurate. Right. My mind's not working too well today. Molecular orbital model is a better estimation of what's happening with any of these molecules. I mean, that's the beauty of it. It covers any one of those. The electron C model only works for metals, and it only works so far, and then it falls apart. But to satisfy the conditions of that statement, that question, silver is the only one that works. All right, how about 10? Which of the following statements about steel is false? All right, so we got A through D, and then E is all of them. All are true. A, B, C, D, and E, all are true. So if we find a false one, then E can't be true. Okay, contains carbon atoms in holes of its iron crystals. That is true. It's an alloy where the carbon atoms are small enough to fit into the voids. So that statement is true. The presence of carbon-iron bonds in the alloy makes steel harder and stronger than pure iron. Yes. The presence of those carbons in those voids, they actually form bonds with the iron, and they prevent, let me back up. Metals, pure metals, are malleable, they're soft. Right? You can take pure iron, I think I said this before, and scratch it with your fingernail. But when you put carbon in there, it prevents those iron molecules from sliding past one another. In other words, the iron has carbons in here. Right? You got iron here and iron here, maybe iron there and iron there, just for argument's sake. And the bonding here prevents those irons from sliding past one another. So it locks the crystal structure in place. That's what makes steel hard. So that one is also true. How about C? Pure iron is relatively soft and ductile because it lacks directional bonding. That's true. It fits that model for the electron C. In other words, the bonding is non-directional. It's just like iron atoms floating in a sea of electrons, right? And they don't, electron comes along and is attracted to that one. Well, there's another iron over here attracted to it too, so there's a mutual support. But that electron is gone, so it has to find something else. So it's bonding in every direction possible. And if we just eliminate that carbon and we just push on it like that, they slide right past one another. It's non-directional bonding. So C is true. How about D? The amount of carbon directly affects the properties of steel. That's true. The more carbon you have in there, the harder the steel. Now, there are other desirable properties that suffer because of that. It becomes more brittle, for instance. But yeah, the presence of the amount of carbon directly affects the properties of steel. The Japanese have known that for centuries when they make their cutting devices, right? The most famous is the katana, right? The sword. They make it out of two types of steel, very soft steel and very hard steel. And they hammer weld them together. They forge weld them together so that if we take a cross section of the blade, right, inside here is the soft steel, and out here is the hard steel. The soft steel gives it toughness. In other words, it can bend and not break. But the hard steel gives it an edge. Now, they may not have known what they were doing, right? The sword making by the masters, at least for centuries, has been an art passed on from master to apprentice. But now we understand on an atomic level why this works. All right. So let's at least go to 1030. I think if we get a couple more of these done, then we'll be in good shape. Let's see, number 11, or maybe get through, let's see. They're subdivided into easy, moderate, and difficult. So maybe if we get down through, lots of easy ones, aren't there? Just a couple moderates. Okay, so that the idea I had in my head won't work. So let's just move along for a few more minutes. Which of the following statements is true of a p-type silicon? p-type silicon. What do we mean? If you have pure silicon, you have a certain number of valence electrons, right, surrounding the silicon atoms. And if you alloy them with some other element that has a different number of valence electrons, then you either create an excess in that localized area or a deficiency, right? So a p-type means deficiency. It's a positive type. So what we need is to put something in this silicon crystal, a substitutional alloy, that is deficient by one or more electrons. So that means if we find silicon on the periodic table, we need to move to its left, right? Fewer valence electrons would give you a deficiency, a positive. And that would be gallium, boron, aluminum, gallium, are just to the left of silicon. So that would give you your positive type, right? If we move to the right, phosphorus or arsenic or antimony would probably be good choices. Phosphorus, arsenic, or antimony. All right, so let's look at our questions. Which of the following statements is true? It is produced by doping silicon with phosphorus and arsenic. This would be an N-type because they have one extra valence electron than silicon does. Right? So A is false. Right? A cannot be true. Protons are the mobile charge carriers. Protons don't move. Right? Your nucleus cannot give up protons without changing the element. Right? So the protons are not going to be carrying the charge. Only the electrons carry the charge. C, it does not conduct electricity as well as pure silicon. Really? Both of them, either type, are better conductors. They're semiconductors. That's why we name them semiconductors. They're not conductors like metal wire would be, like copper wire would be a conductor. And they're not insulators like, well, I don't know, pure silicon would be an insulator. Right? There's no mobile charge there. Right? So it does conduct electricity as well as pure silicon. In fact, better than pure silicon. So this one's false. How about D? All are true? No. All are false. That one's it. None is true. Excuse me. All are true? No. None is true. That's correct. They're all false. All right, let's see. About 14. A solid crystal of sodium chloride. Sodium chloride. What does a solid crystal of sodium chloride look like? Well, if we could get down small enough, right, you'd see that the overall ratio of sodium to chloride in this crystal would be 1:1. So for every sodium, you've got at least one chloride. Well, in fact, you've got chloride here and chloride here and chloride here. And then you've got a chloride out here and chloride behind it. And each chloride has a sodium around it. So you've got this network. And the it has a simple cube unit cell. Right? So you're going to have chlorides would form the cubic network. here, because they're the biggest. And then the sodiums would be, they would be fit in the voids, right? We couldn't put just one sodium here, right? That wouldn't be enough for the charge balance. We need 1, 2, 3, 4, 5, 6, 7. Well, actually, there's one chloride for each of these unit cells. So the voids would have to have one sodium for each of the unit cells. But to answer this question, in order to conduct electricity, you need mobile charges of some kind. Electrons in a metal, like copper metal, electrons can move. Or if you have mobile ions some other way. But if they're locked into a crystal structure, they cannot move. That means sodium chloride is an insulator. It's both an electrical insulator and a thermal insulator. So that's not everything that's addressed in this problem. We're talking about melting point and hardness, right? Ionic crystals are usually hard, right? So if we're using a test-taking technique, start with the first one. Which one's hard? B and D are hard, right? We know that sodium chloride is not soft, so A, C, and E, we throw them out. Then we go to the next one, high melting point. For B and D, yeah, they're both, right? So we've got to stay with those. Then we go to the next one, a good electrical conductor or a poor electrical conductor. So D has to be the answer. Okay. All right, that's 14. Let me see. How we doing? We're doing real good on time. What if we finish this page and then we'll call it quits? 15. That'll put us in pretty good shape for Thursday. Which of the following has the highest melting temperature? Well, let's see. We have water, we have carbon dioxide, and S8, and MgF2, and we have P4. Carbon dioxide at room temperature is a gas, right? So its melting temperature is going to be really low. In fact, well, solid carbon dioxide is minus 78.5 degrees Celsius. And I think we can turn it into a liquid at a slightly higher temperature, like minus 75. Right, so it's still going to be very low temperature. So we can count carbon dioxide out for the highest melting point. Water, we know water melting point is 0 degrees, right? And in addition to that, these are molecular solids. When they form a solid, molecule, 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 molecule. The only forces that they have available to them are either dipole-dipole or London dispersion. Right? So if we can find one that has the potential for higher forces, then we've got our answer. And here it is right here. This is an ionic solid. And the attraction, the electrostatic attraction between magnesium ions and fluoride ions is much stronger than it is. Well, this is nonpolar, that's nonpolar, that's nonpolar. This is polar, but it's still only dipole-dipole hydrogen bonding. And the forces between these ions is much, much stronger. Okay, so there's our answer. That has the highest melting temperature. Now, the lowest melting temperature would be this gas. Right? At room temperature, that's a solid, that's a solid. And this is a liquid. This is a gas. So it's going to have the lowest melting temperature. All right, 16. Which of these statements is false? Diamond is a covalent crystal. Is that true? Yeah, every carbon atom in the diamond is bound to every other carbon with a covalent bond. It's a covalent crystal. Okay, so that one's true. B, the size of the unit cell of lithium and cesium is the same. Does that make sense? Look where lithium is. It's way up here. Cesium's way down there. So what happens as you move down a period? You get bigger atoms. So when you form them into a crystal, the unit cell has to be bigger for cesium. The cesium unit cell has to be bigger than lithium simply because the cesium atoms are huge. Right? You can't pack them close enough. Packing model, right? You have to make accommodation for the size of the balls. And the cesium balls are a whole lot bigger than lithium balls. So this one is false. Let's see, what are our choices? None of the statements is false. Oh, we found a false one. There we go. So that one's false. The rest of them should be true. Molecular crystals usually have low melting points. That's true. Yeah. Metallic crystals are usually good electrical conductors. Metallic crystals. That is when you have the metal atom fixed and the electrons are free to move. That's true. All right, so we found our answer. B is the answer. And then 17, and that, I think that's the last one on this page, and we can call it quits for the day. Okay, how would you expect the melting point of carbon tetrachloride to compare to sodium chloride? Carbon tetrachloride and sodium chloride. Comparing melting points. Well, this is an ionic compound. This is a molecular compound. It's non-polar, right? So it only has London dispersion forces available. Right? I would expect the melting point for this one to be much higher. But does it ask for a reason? It should be lower. So this one is lower. But does the reason make sense? It's lower because sodium chloride forms an extended ionic crystal lattice, whereas carbon tetrachloride is covalently bonded small molecule. Yeah, that's true. A is true. And we don't have any wonky ones down there, so I think we found our answer. It's not going to be similar because they're not both ionic compounds. So B is false. B cannot be true. It should be higher because the bonds are stronger due to a higher charge of carbon. Okay, we're getting really ridiculous now. It should be higher because carbon tetrachloride is larger than sodium chloride. That doesn't work here. That's ionic, and this is nonpolar molecular. Now, if we were comparing the two nonpolar moleculars, and we had one that was, say, if we had two carbons, like this, like this, like this, that, then the melting point of this would be at a higher temperature than that one. Because this is a larger molecule, it's still nonpolar, but it's larger than that one, and the London dispersion forces would be larger for this one, simply because of its size. Okay. But that's not what we have. We're comparing a molecular, nonpolar molecular compound with an ionic compound. So D can't be true either. It's not possible to say anything about their melting points without more information. Well, that's patently false. We just said a whole bunch about them without any more information. All right. I think that's the last one that we're going to do today. If that's the end of, oh, one, nope, two more, sorry. Jumping the gun. 19. At normal atmospheric pressure and temperature of 0 degrees, which phase of water can exist? We're at 0 degrees C, at 1 atmosphere pressure, right? And this is water. So what phases can exist at that temperature? I mean, is it a single phase or can we have more than one phase? This is the melting point of water, right? If we're actually at 1 atmosphere pressure and 0 degrees, theoretically, you can have both the solid and liquid together. Right? If we drew the phase diagram, pressure, temperature, there's our triple point. Go like that, go like that, go like this. Then this is a solid, this is a liquid, this is a gas. So anywhere on this line, if we're at 1 atmosphere, the temperature is going to be 0 degrees. And this line defines the phase where both phases occur at the same time. This one's solid and liquid at the same time, and any combination of pressure and temperature along that line, you have both phases, solid and liquid. Okay? So, did I answer the question? A, ice and water. 20. This should be our last one. Which of the following processes must exist in equilibrium with the evaporation process when a measurement of vapor pressure is made? So, say we have a flask. We've got a stopper in it. And we've got a liquid here. And we're going to measure vapor pressure. Which of the following processes must exist in equilibrium? Okay, so if we've got a headspace up here and we've got a liquid down here, then the liquid's going to do what? It's going to evaporate. And when you get enough molecules up here in this headspace, they're going to do what? What's the opposite of evaporation? Condensation. So those two processes, for a stable equilibrium situation where we can measure vapor pressure, then the rate of evaporation is equal to the rate of condensation. So that makes E the answer. And we could make up something for anything. How about, here's a squirrely one, just for argument's sake. We're still going to measure vapor pressure. But suppose we have a block of solid carbon dioxide. Right? What's it going to do at room temperature? It's going to vaporize, right? It's going to sublimate. Well, what's the returning process? Deposition. So if those two are in equilibrium, then we get a vapor pressure. Okay, I think that's it for today. Yeah, we're going to pick it up with 21. Let me mark my. All right, before we get into the review, I want to share, if you haven't seen this yet, point this out to you. Share that one. And then to put it up on the screen. Recognize that as a crossword puzzle. Okay, that's chapter 11 crossword. You notice that right down here, I've made the correction already. 27 down only had 2 places. And if you try to answer it correctly, there's not enough room. You need 3 places. Okay. So if you've already done it and you put something in there that looks like the right answer, I'm going to give you credit anyway. But if you haven't done it, then this new one is in bright space and you can work from that one. Okay, let's stop that share and let's get back to business here. Let's share this one. There we go. I think we left off with 21 was our next one, number 21. So, and I haven't posted the video yet. I think what I'm going to do is I was going to cut out part 1 of this review of the video and splice it together with part 2 and make this one single video. But that should be up, what's today, Thursday? I should be able to get that done tomorrow. I haven't posted the review for the lab either. So if you missed the, let's see, I think you were the only one missing Tuesday, right?
I don't do the computer.
You were on the computer? Oh, 1 second. Because if you were here, then I want to be sure I got you in the. There's 23rd, there's 25th.
I was the one that missed Tuesday and Thursday of last week.
Well, I've got you down for both days. Were you Zooming?
Yes, I was Zooming.
Yeah, okay, that's fine.
Okay.
I got everybody credited with attendance. Okay, well, no, that's good. Because then I don't have to worry about you getting the introductory for the lab. Okay, let's get on with number 21. By the way, this is 2 chapters. Yep. This is chapter 10. I don't know if I did that for the first part. The reason I need to do that is because chapter 11, I start renumbering. Okay, 21. You're given the following boiling point data. Which one of the liquids would you expect to have the highest vapor pressure at room temperature? So what's the relationship between boiling point and vapor pressure? Think about it in terms of intermolecular forces. If the boiling point is high, the intermolecular forces are also high. And high intermolecular forces holds those liquid molecules more strongly, so they don't vaporize as readily. So as the boiling point increases, vapor pressure should go down. It's more difficult. They need more energy to leave the surface of the liquid into the vapor phase. So this one, these are inverse of each other. Let's see, they write that proportional. That. That's the way we do it in symbology. Vapor pressure is inversely proportional to boiling point because of the way the intermolecular forces work. Right. So I'm going to forget. Okay.
Oh, my change?
Yeah, that's your change.
Great.
Okay. That's 21. Let's see what 22 has in store for us. Which one of the following decreases as the strength of the attractive intermolecular forces? Well, that's 21 in different terms, isn't it? As the intermolecular forces increase, As forces increase, what decreases? Well, vapor pressure. Right? So that would be E, vapor pressure of the liquid. Two ways of asking the same question, 21 and 22. Let's see, that's not going to work. I have to scroll. There we go, 23. In which of the following processes will energy be evolved as heat? All right, so remember when we've got, let's see, how did I arrange this? Gas up here, and let's see, solid over here. I think that's the way I had it arranged. Liquid over here. As you go straight from solid to gas, what's that called? Starts with an S. Sublimation. Okay. This is sublimation. Now, is this an exothermic or an endothermic process? In other words, if we go from a solid to a gas, you have to break bonds, right? That means energy has to go in. So this is endothermic. Right? So that means the reverse, deposition, is exothermic. As you go from a gas to a lower energy state, which would be, these are moving lickety split. They're going all over the place. And when they become a solid, then they have to give up that energy. That's exothermic. Now let's see, am I getting warm? Which of the following processes evolved as heat? All right, this would evolve heat, deposition. It's not there. All right, so let's try this one. Solid to liquid is vaporization, right? And this is also endothermic. Okay, going, yeah, solid to liquid is endothermic, and backwards is condensation. So this one would be exothermic. Right, is that up there? Evolve heat, condensation. Nope, that's not there either. All right, liquid to gas. Okay. Go this way. And that's, oh, excuse me. That's not vaporization. Let's see, boiling, melting, melting is better. There we go. This one is vaporization. And that is, you have to put energy in, endothermic. Right? So the opposite direction would be what? Well, that's not condensation either, is it? This is condensation, exothermic. Is that one up there? Okay. What's crystallization? This would be crystallization, would it not? Liquid to solid. Actually, that's a poor choice of words. Because you can make crystals from a liquid or you can make crystals from a gas. Can't you? Right. So, well, either one of those would be exothermic. So I guess deposition and let's see. I want to say fusion. Liquid to solid and fusion. These are both exothermic, and I think they're classifying either one as crystallization. Yeah, I think that's why I put this one in here, because of that term. We haven't covered that term. It could be confusing. But crystallization can happen either from a liquid to a solid or a gas to a solid. Yeah. What do you need? Study guide.
The review paper.
Oh, you both need it?
No, I got mine.
Okay. Let's see. Out of the lab.
I got the lab paper.
Okay. Here. I'm gonna let you dig.
That's fine.
Everything you need should be in there. Class 20, any questions about this, or did I thoroughly confuse you?
Thoroughly.
All right. The idea is when you, when the molecules, when you break the intermolecular forces to a phase change, you have to add energy, right? So anytime we go from a solid to a gas or a liquid to a gas or a solid to a liquid, you have to add energy. That's endothermic. Exothermic is just the opposite direction. The terminology is the problem here. Crystallization could either be fusion or deposition. Maybe solidification, another name for fusion. Okay, so the answer would be crystallization. And let's see. I jump down. No. Oh, it's not behaving. All right, we'll do it manually. 25. Let's kind of get the whole thing. Yeah, get the whole thing on there. 25. All right, you'll recognize this as a phase diagram, right? Where you have pressure on the y-axis, temperature on the x-axis. And let's see, we're going from all right, I think we're going to go up to here. And then this line has a positive slope. And then this one, actually, it kind of jinks a little bit, which is not unusual. Right? We like to portray them as uniform, but you can get these odd movements here, like this, like that, and then like that. Okay, and on this side is the solids, this is the liquid, and this is gas. Under these conditions, low pressure, higher temperature gives you gas. Let's see, and that goes out to maybe right there, because that is another point. This is the triple point, remember? You can have all three phases together at the same time if the temperature and pressure are exactly those values. If they deviate, any one of these deviates from those, then you're into one of these other only two-phase situations along that line. Anywhere along that line, the temperature and pressure will give you liquid and gas at the same time. Anywhere along this line, at those temperatures and pressures, solid and liquid can occur at the same time. And for this line, solid and gas can occur at the same time for this temperature and that pressure. Okay, that's how to read it. Now we got another line here that shows us, position this correctly, that shows us 1 atmosphere. I'm going to put a dash line here. This is 1 atmosphere. Okay. Now for the question. The diagram is qualitatively correct for water. Okay. What's peculiar about water in the phase diagram? That line right there. Most substances, in fact, I haven't found any but water to do it. There probably are some, but they're kind of exotic. As you increase the temperature or increase the pressure, either one, you go from solid to liquid or liquid to solid. As you increase the pressure on this liquid, If you're at the same temperature, right? Right here, and you increase the pressure, you're going to get a solid. But with water, it goes back the other direction. So at this temperature, as you increase the pressure, you go from solid to liquid. Okay, that is not water because of this slope. For water, the solid liquid phase line is a negative slope. Okay. I don't hear any objections or questions. Are you just taking it on faith? Yeah, that's okay. All right, so A is false. Let me remove some of this confusion here. All right, so A is false. That's not water. The diagram B, the diagram shows that the melting point of the solid increases with increasing pressure. So what would be the melting point? Solid to liquid, right? So solid to liquid, it says that the diagram says this line determines the melting point, right? Depending on the pressure. So if the pressure increases, the temperature has to be higher to reach that line, right? That's the way you read the graph. As the temperature increases, the pressure is increasing. It's a positive slope. The diagram shows that the melting point of the solid increases with increasing pressure. That's true. It does. So E says none of the above statements is correct. We found one that was correct, right? So if you're on a test and in a hurry, you got your answer. We could go through the others. The triple point, right, shows above 1 atmosphere. No, triple point's down here. 1 atmosphere is up there. So C is false also. I guess I might as well go through all of them. The diagram could represent the phase diagram of carbon dioxide. Okay, what happens at 1 atmosphere pressure for carbon dioxide? If it's a solid, then 1 atmosphere will allow it to go from solid to gas this way. Right? So 1 atmosphere is in the wrong place. It needs to be down here for carbon dioxide. All right, so let's see. Both of these are false. Okay. Moving on. That was 25. Oh, another phase diagram. Aren't we lucky? Let's see. Can I get them all on there? Yep. All right. This one has, rather than just a general scale for temperature and pressure with that 1 atmosphere identified, this one actually has values associated with the phase diagram. Right, so we got 0, 100, 200, and 300. There's 0, 100, 200, 300. K. Right? Yeah, temperature and K. Okay. How about pressure? We go up about the same distance here. And that's a half of an atmosphere. Then a whole atmosphere will be here, and 1.5 will be here. Yep, this is pressure in atmospheres. Okay. So now, where's the triple point? The triple point looks like it's just short of 200 and just above 0.5. Or 200 above 0.5, about right there. So our line's going to go from here to here, and then it's going to take off and go here, maybe up like that a little bit. Oops, that's too far. Try that again. 1 atmosphere is going to go like that, and then it's going to go like that. Okay, and from the triple point, we're going to go up this. Okay, so there's our diagram. What's the question? This compound Q, you wish to purify a sample of Q that was collected at 1 atmosphere pressure and 100 K. So here's where we're starting. That's where the substance was collected as a solid. Okay? But anytime you create something and you collect it at a given temperature, pressure, there's always the risk of contamination. So we want to purify it further. And one way to purify it is, according to this problem, we want to sublime it. In other words, go from solid to gas. And then when the gas comes off, we collect the gas and deposit it as a solid on another. If it's a small amount, well, we might use a cold finger, they call it. So you have a big tube and then a smaller tube inside, and the smaller tube is refrigerated. It's got something really cold in it. And as the solid sublimes, it collects on the tube. Okay, and then you've purified it, or you've cleaned it up anyway. All right, so the idea is we want to sublime it in order to purify it. So which one of these, A through E, would be the best way to do it? Right? I like E. Abandon your attempt. There ain't no way, right? That's false. We're going to be able to do it. All right, how about A? Okay, increase pressure to 1.5 atmospheres. So if we're starting here and we increase to 1.5 atmospheres here, then increase temperature to 300. Then we would go over to 300. What's that going to get you? Well, it's going to go through liquid, and then it's going to go into the gas. Actually, it's going to go into the critical region, right? This is the critical point. So it's going to be in the critical region. It's going to be gas and liquid at the same time, right? So we're not going to collect any. Right? That's false. A is false. Okay, how about B? Increase temperature to 300. Right? So here we got another option. We're going to go from here, increase temperature to 300. Right here. Keeping the pressure at 1 atmosphere. Okay. That puts us possibly in the gas range. You're not going to collect any solid there, right? If you want to sublime it, you've got to be able to recollect it. Right. So at that point, it doesn't tell us that we go anywhere from here. All right, so that was false. How about C? Lower the pressure to 0.5 atmospheres. Okay. So if we lower the pressure to 0.5 right here, and then what? Increase temperature to 200. Yeah, you're going to keep it a solid and then go straight to gas here. So now that we've got it as a gas, we leave all the contaminants behind as solids. But then we've got to, I think it left out a step, right? Because once you get it in the gas, if you want to recollect it, now you've got to cool it down again. Right? Once you've got the gas here, then you've got to cool it back to this region to make it a solid again. But that looks like it's the best answer. So far, that was true. Let's see if D's any better. Increase temperature to 300. Right? If we go from here to 300, then lower pressure to 0.5. Well, what you're doing is you're crossing through liquid, and we don't want to do that because that's not sublimation, that's melting. We're going to melt it, and then we're going to vaporize it. So for all we know, the contaminants would vaporize just as quickly. If we collected everything in this region, then it's logical to assume that if we go through the liquid and into the gas, then we're also going to carry those contaminants with us. Right? So I think the best answer is C. If that makes any sense. Hope it makes some sense. All right, 26. We'll skip a couple of other, and we got another phase diagram. Given the phase diagram below, which of the following statements, A through D, is false? Okay. My guess, based upon, so we're going here, and then we're going here, and we're going here. This is pressure and this is temperature. My guess is that this is water, simply because that's a negative slope. So which one satisfies? Well, let's see. Which one is false? Okay, so we're going to find, hopefully, none of the above statements is false. This says that they're all true. So let's see. The solid has a higher density than the liquid. Okay, so this is the solid, this is the liquid, this is the gas. Okay. Well, if this in fact is water, then we know that's not true. The liquid has a higher density than the solid for water. That's why ice floats. Right? The solid is less dense. So A is true. Which of the following statements, A through D, is false? Oh, that's false. Excuse me. A statement as read is false. At some constant temperature, the gaseous substance can be compressed into a solid and then into a liquid. So at some temperature, you can pressure it into from a gas to a solid and then into a liquid. That's true. When phase A is compressed at constant temperature at point X, oh, so we got point X way out here. Right. No change is observed. That's because you're in the critical region out here. So you pressure here, right? Can't see any difference. Right? Can't tell the difference between liquid and gas. They're both fluids, but if you know, that's one thing I need to include in the PowerPoint slide set is to get you. I've seen these videos of a substance that's being compressed and heated at the same time, and you can see the two phases, gas and liquid, and then gradually they just disappear. And it's all one phase. Make note. Yeah. Not going to do you any good, but maybe the next class will appreciate it. So what did I say? When phase A is compressed at constant temperature X, no changes observed. That's true. Because you're in the critical region. When heated at 1 atmosphere, this substance will first melt and boil. Heated at 1 atmosphere. Oh, there's 1 atmosphere. Right about here. So if it's heated at 1 atmosphere, it's going to go through solid, liquid, gas. That's true. So all are not true. Only A is false. All right, let's see. And oh, okay, I'll get that down there for me. Oh, This is moderate, we're changing it. That was easy. This is moderate. I need to go in and renumber these things. Then I gotta go renumber all my worked problems, my handwritten problems. That's probably why I haven't done it. So this is moderate 1. Which of the following is the correct order of boiling points for KNO3? Let's see. Methanol. That's the kind that makes you go blind when drinking. C2H6. C2H6. That's ethane. This is ethane. This is methanol. That's potassium nitrate and neon. Okay. We should find boiling points for these compounds in which order? All right, it looks like we're increasing boiling points to the right. So the lowest boiling point is going to be the one with only London dispersion forces available. All right, do we have anyone? Right there. And right here. All right, this is C2H6. This would be your Lewis dot structure. Only it doesn't have any dots because there are no lone pairs. Right? These are both nonpolar. But this neon is a smaller atom than this molecule, which means this one has larger London dispersion forces available. Right? Remember, the larger the molecule and the larger the atom, the higher the probability you have for uneven distribution of electron density on an instantaneous basis. So if this is bigger than that one, then you have more likelihood that you can spread those charges apart temporarily in order to create opposite charges in nearby molecules, right? But neon is smaller than that one. So this one we can have the lowest boiling point because the forces that are holding it together are the weakest. So neon will be first, and then ethane. Okay, now we have to decide between these two. What are we talking about here? Well, this has hydrogen bonding available. Right? This molecule is polar. This is ionic. It would have the highest boiling point because these are complete ions. Right? This plus and that group is a minus. This one has no charge, no complete charge. It only has hydrogen bonding available. So it would come next. And then, oops, the other way, sorry. There we go. And then KNO3 would have the highest boiling point. So that one would be, looks like D. Okay. That was moderate 1 for chapter 10. Let's see, moderate 4. We're actually going to have to do some calculations. Assume 12,500 joules of energy is added to 2 moles of water as an ice sample. Okay, so we got ice, water. Okay, there are 2 moles here. And they tell you so you don't have to calculate it, which is 36 grams. Okay, we're going to add 12,500 joules. And this is at 0 degrees. At 0 degrees C. Right, and they're telling us that this is all ice at 0 degrees. Now, at 0 degrees in 1 atmosphere, it's possible to have solid and liquid. Right? Nobody disagrees with me. It's possible to have both, but this is telling us we're starting at solid. All right, so let's look at the phase diagram. Let me put it over here. This way. So this is adding heat going this direction. And this is temperature in degrees C. Okay. So we're going to go up to, we're going to start off as a solid. And then when we get to the melting point, right, temperature stays constant while we have solid and liquid. And then once we've got all the solid melted, the liquid starts to heat up. And the liquid then is by itself heating up until we get to boiling point. And now we've got liquid and gas. And then once we've got all gas, we can continue heating the gas. Right? Sometimes it's called superheated steam. The industry uses that. Wherever they need heat transferred, they just pressurize the steam and heat it like crazy, and it'll carry lots of energy from one point of the plant to the other. Okay, so where are we starting here? This is at 0 degrees, solid only. So at 0 degrees, we're right here. Like this is 0. This is 0 degrees. And this is 100 degrees. Okay. All right. Sometimes pictures help. The molar heat of fusion is 6.02 molar heat of fusion. Let's see. We didn't talk about this, did we? No, we just talked about this one. Change in temperature equals K freezing point times molality. Well, you can also, if you have the molar heat of fusion, in this case 6.02 kilojoules per mole, molar heat fusion equals 6.02 kilojoules per mole, right? What that means is when we're at this point, how much energy does it take to change a mole of solid into a liquid of the solid, the liquid of the compound or the substance? Well, it takes that much energy to go from here to here. This would be, I'm trying to remember the symbol. Delta H, actually, yeah, molar heat of fusion is that distance. To go from the solid to the liquid. And so all the energy that's going into this solid is converting it to liquid until we get to this point. Now all of it's liquid. Okay, so how much heat does it take to go from solid to liquid? Well, 6.02 kilojoules per mole, but we've got 2 moles, right? Right. So this is times 2 moles, leaves us 12.040 kilojoules, right? Because moles cancel. So that's how much energy it takes to go from solid to liquid. Do we have any left over? Yeah, well, kilojoules is what? 12,040 joules. 12,040 joules. What do we got left over? 0, 6, 4. 460 joules, right? And we still got that much energy left. So we can heat the water up. All right, so now we go back to this one. And this one is where we This is where we show the change in temperature. Let's see, are we going to be able to tell the concentration? Oh, we don't need concentration. We need, because this needs to be wow. Oh. This isn't a solution. Right. This is not a solution. So actually, this is not the formula we need to use. We've got 460 joules. How much energy does it? How far is that much energy going to take us? Right. This is a conversion factor problem. That many joules, we want to convert it to change in temperature. Right. So this many joules times 4.18, actually divided by. Let's put it this way. Joules and I'm afraid I'm confusing everybody. We got 460 joules. If we have 4.18 joules per gram degree C, 4.18 joules per gram degree C. In order to cancel the joules, we need to divide by 4.18 joules per gram degree C. Right, that will cancel the joules. It'll put grams per degree C on top. Let's do it step by step. I think that'll make more sense. Okay. So 460 divided by 4.18 is 1.10 what? Grams degree C. Okay. How many grams do we have of our substance? We have 36 grams. So 36 grams needs to be divided into this in order to cancel the grams, right? So, is that right? No. 110. Right? Yeah. I conveniently ignored the exponent. So 36 into 110 is what? Is 3.06. Or let's see, 3.1 actually. 3.1. Left over is degree C. So that's how many degrees we're going to change the temperature. We're still at 0 here. But now we're going to move it by a change in temperature equal to 3.1 degrees C. Right? Is that going to get you anywhere near the boiling point? No. The only phase that's now in that container is liquid. Right? We didn't have enough energy to take it to gas. I hope when I work the problem out by hand on the review document, I hope I explained it better than I did here. So check it out and see if it bears any resemblance to this. Let's see. Now we're into difficult. All right. Number one? Yeah, number one. Okay, a crystal was analyzed with X-rays having 2.33 angstrom wavelength. So the wavelength of our X-ray is 2.33 angstrom. What's an angstrom? Nobody remembers. We didn't hammer this one too hard. An angstrom, 1 angstrom is equal to 10 to the minus 10 meters. All right, so if we want to go ahead and convert this to meters, actually, we don't need to. And I'll explain why in just a second. The angle of the first order diffraction, where n is equal to 1, theta for the first order is equal to 19.2 degrees. 19.2 degrees. What would be the angle for the second order? Right, for n equal 2, the question is, what's that angle? Okay, this is all based upon the Bragg equation. To be sure it's in the useful information because you're going to need it. Here it is. Yeah, n theta, n lambda 2d sine theta. Sine theta. Right. D, remember what D is? The distance between the layers of the crystal. Okay. So there are 2 ways that we can work this. We know this is the lambda for, well, actually that's the same wavelength we're going to use for both of them. Remember when I described the experience with the clays and I had that device? You could watch the arm. It was an ancient device. And you could watch the arm move as it scanned through the different angles. And then it had just a strip chart recorder on the side. And every once in a while it'd go like that. Then you go along and then a little first order, second order, third order, different angles. Having to do with constructive and destructive interference. So we know n, got that one, we got this one here, we got this one here, we can find out that one. Well, for this particular sample, is D going to change? No, D is going to be the same. So we have 2 options. We can solve it for D, and then we can go back and put in a different n along with the wavelength and the D value we just determined and calculate the theta. That's one way, 2 steps. Or we can solve the 2 equations if we just make this one 1, that one's the same, this one's the same, this one's 1, and then set up another equation over here, n2, with the same x-rays and the same distance, and then sine theta 2. And we can set everything equal to D on this side and that side. Right, since D is the same for both of them, we can set those 2 equations equal to each other and solve for this unknown and then plug in the numbers and do it in one calculation. That's the other option. Right. But if it makes more sense, we can do sequential calculation. I think that's the way I did it in the worked problems. So we'll do it that way. All right, so to solve the first one, we're going to have 1 times the wavelength and then 2 and D. What's D? We don't know yet. Sine theta, 19.2 degrees. So we're going to solve for D. And let's go ahead and do that. D is here, and that means 2.33 angstroms divided by 2 times sine 19.2. There we go. So now we can find out what D is. And what are the units of D going to be? Well, degrees are dimensionless, right? And that has no dimensions. So D is going to be in angstroms. So let's see, 2.33 divided by 2 and 19.2, and take the sign of it. See if I find my sign key. Here it is. Divide that in. So the distance between the crystal layers is 3.542 angstroms. Okay. So now we can take that value, and over here, we've got this one is 2 now. This one is the same angstroms. That's 2. Now we know what D is, 3.542 angstroms. And then the sign of the second order angle. Okay. So if we keep this on one side, because that's the unknown, and move these over here, then this one cancels that one, right? Goes into the denominator. This one now is angstroms divided by 3.542 angstroms. So that becomes a dimensionless number, which is good. And then sine theta. 2. Okay, so let's see what that value is. I still got that number in my calculator. 2.33, and then divide that into it. So this is 0.6577 equals sine. How do we find theta? Has anybody had trigonometry here? No? Okay. The term for finding this value, finding that value from this value is the arc sine. Right? So if we wrote it correctly, it would be theta 2 equals the arc sine of 0.6577. So that, and on your calculator, that value is going to be probably a shift above the sine key. Like a sine. On mine it says a sine, arc sine. So 0.6, it's already in my calculator, so I'm just going to get that key. And that gives me 41.1 degrees equals theta 2. Okay, so that answered B.
So that equation is going to be in like useful information.
Yes, the Bragg equation. It's right here in the middle of the, almost in the middle of the page. Yeah, it's identified as the Bragg equation. I know some of those equations, I don't put a label on them, but that one I figured it could use a label. And that was correctly placed in the difficult section. Anybody plan to take trigonometry?
Hopefully not.
No? Okay. Well, huh? I didn't think so. But I'm not a good yardstick to use. I like this stuff. Number 2. Chromium metal crystallizes as a body-centered cubic lattice. A body-centered cubic unit cell. All right. And we're talking about chromium. If the atomic radius of chromium is 1.25 angstroms, radius equals 1.25 angstroms, we will need to know the conversion for this one. What's the density of chromium metal in grams per cubic centimeter? So we're looking for density equals something in grams per cubic centimeter. All right, so working this problem, we go to the end result. Read it backwards. That's what they say about when a new rule is promulgated by a government agency and it has to be out there for review. The best way to read it is to go to the end and start reading backwards, because the really meaty stuff is at the end. Although sometimes they have an executive summary at the very beginning. Start there. Anyway, to solve this problem, we need to find density. So we're going to need two values. We're going to need the mass of chromium and the volume that that mass represents. That's where this unit cell comes in. Okay, so our unit cell is going to be a cube right there. Right, we're going to have chromium here, chromium there, chromium there, 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 and we're going to have a chromium right in the middle, body-centered cubic. Okay, so in order to tell the volume, we need this distance right here. Let's see, what are we going to call it? X. Call it X. What's the side? What's the edge of that cube? And then if we know that, all we have to do is cube that value. Right? So the relationship here is between the radius of chromium and in that unit cell and X. Right? And that should be in useful information too. There it is. Just above the Bragg equation, body-centered cube edge. Oh, they're saying A. Okay, so let's be consistent. We're calling this A. Okay. So that edge, that A, is equal to, see, I don't even have it memorized, 4R divided by R divided by square root of 3. So as long as we know this, we can find A. So it's going to be 4. Let's see, we want to go ahead and put that in centimeters. Yeah, let's convert R to centimeters first. Because we're going to need cubic centimeters anyway. So if R is 1.25 angstroms, then, but meters, it would be that times 10 to the minus 10. Right, so we can get rid of this times 10 to the minus 10 meters. Now we can convert it to centimeters. Right? 1 meter equals 100 centimeters, right? So R then in centimeters is minus 10 and 2 is minus 8, right? 1.25 times 10 to the minus 8 centimeters. Right, that's R. Now what's A? Well, A, let's go over here. A then is equal to 4 times that R value, 1.25, oops, dyslexic, times 10 to the minus 8 centimeters. That's right, divided by square root of 3. Yep. Okay, so let's find out what A is. 25 exponent minus 8 times 4, and then square root of 3 divided into that. We have 2.887 times 10 to the minus 8 centimeters. That's equal to A. And so the volume is going to be equal to 2.887 times 10 to the minus 8 centimeters cubed. The volume of a cube. So I've already got it in my calculator. I just need to put in the power. There, this key right here. And that's 2.406 times 10 to the minus 23 cubic centimeters, right? Anytime you do something to the number, you do it to the unit also. Okay, so we got our volume. Now we need mass. What's the mass? Well, what's the mass relative to this unit cell? How many chromium atoms are in that unit cell? Remember? Let's go through it again. How many are in a simple cubic? You've only got the corners covered. 1/8 of each one, and there are 8 of them, so there's 1 atom per unit cell for a simple cube. For a body-centered cube, we just add a whole one, so that's 2. Right? Face-centered cube would be 4. So we have 2 atoms of chromium. Let's see, let's do it over here. So we can continue our calculations over there. Right? 2 atoms of chromium. We want to find out how many grams that is. Right? What's our relationship? The mass to numbers of atoms. Molar mass, 52.00 grams per mole. So how many moles is 2 atoms? Right, we need 6.022 times 10 to the 23rd atoms, right? That cancels that, leaves us with moles. Okay, so now that we have moles, I have to come down here. We want to get rid of moles and leave us with grams. So it's 52 grams per mole. Now we just say, that's the thinking part. 2 times 52 divided by Avogadro's number. And that should be the mass in that unit cell. Okay? All right. So 2 and 6.022 exponent 23 divide, and then times 52. So this is 1.727 times 10 to the minus 22 grams. Now the density. Now we can calculate the density. Let's do it down here. Density. Mass per unit volume. There's our mass, 1.727 times 10 to the minus 2 grams. And there's the volume that mass represents. 887 times 10 to the minus 8. Oops, sorry. You guys were going to let me do that, weren't you? 2.406. That's just the edge of the cube. 406 times 10 to the minus 23 cubic centimeters. So our units are right, grams per cubic centimeter. Let's see, just swap places for those and divide. So I get 7. Let's see. I'm limited to 3 significant figures. 1/8 gram per cubic centimeter. That's B. B's in. Okay. Eyes starting to glaze over. This is, the real problem here is not so much the math and the concepts, it's the speed. We've only got 10 weeks to get through this stuff. You don't have a lot of time to absorb it. That's the big problem. All right. Let's see, we have any more difficulties in chapter 10? Or is that enough? Okay, chapter 11. Okay, I think chapter 11 is going to be easier to follow. And how long do I have? Hour and 10 minutes, hour and 9 minutes. Chapter 11. And we're starting off very easy. Okay. In a 0.1 molar solution of sodium chloride in water, 0.1 molar sodium chloride aqueous solution. There. Which one of the following will be closest to 0.1? All right. What does this mean? Molar. It means 0.1 moles per liter of solution. At that concentration, the added sodium chloride is not a significant boost to the mass. Just 0.1 mole of sodium chloride is what? What's 1 mole of sodium chloride? 23 grams per sodium, and chlorine is, I know this, 3545. All right, so that's 5, 4, 8, 5. 58. Be better than that. Grams per mole. Right? So that is what? 0.1 mole is 5.845 grams per liter. Right? That's 1/10 of a mole. The point I'm trying to make is, how much is a liter of water? Approximately 1 kilogram, right? 1,000 grams. So we're only adding 0.58% to its mass. That means that this value is approximately 0.1 molal, because that would make it 0.1 moles per kilogram of solvent. Okay, so they're very close together, very close values. Now we could go through the others if we had time. Mole fraction. What would be, and I think I did in the work problems. I went through each one and calculated them and find out that the closest one to molarity is molality. Right. That was the point of this problem, just to prove to you that molality and molarity are very close together in size. The only difference is when temperature changes, that one changes. When temperature changes, that one does not. Right, so I'm going to let it go there. If you want to calculate the rest of them, be my guest. Right, you have the formulas, you know how to calculate them. Right, mole fraction, you just find out how many moles does that represent? Well, 0.1 mole in a liter. What's a liter of water? Right, how many moles is a liter of water? That's a question. Mass fraction is easier to calculate, right? Because the total solution is about a kilogram divided by 1. So mass fraction, actually mass fraction would be that 5.8 divided by 1,000. Right, so it's going to be a really small number. Molality is the closest one. Oh, I didn't write the number there, did I? That was number 1. So number 2. Which of the following concentration measures will change in value as the temperature of the solution changes? The one that changes with temperature is the one that is expressed as volume anywhere in its calculation. Right? If it's only mass in the calculation, if it's only moles in the calculation, then the value will not change with temperature. Right? Because those numbers of things, masses of things, they don't change with temperature. Only volume changes with temperature. So mass percent, which one changes with temperature? A, no, mass percent doesn't change with temperature. Mole fraction does not change with temperature. Molality does not change with temperature because it's ratio to the mass of the solvent. Molarity. That's the one that changes. Okay. Let's see who's next. 3 and 4. Squeeze 3 and 4 in there. Which of the following chemical or physical changes is an endothermic process? So we're looking for endothermic. Okay, evaporation of water. Water's going from what? Liquid to gas. That's endothermic. Oh, we found our answer. Because it says none of these for E. Combustion of gasoline, which is primarily octane plus oxygen, yields carbon dioxide, water. That's not balanced, of course. This is exothermic. Right? If it weren't exothermic, the engine would have run. Right? If it got cold when it combusted, you know, that's an interesting question. If it were an endothermic process, could we turn that into some usable? I bet we could. It'd be like a reverse heat engine. Yeah. Anyway, right. So this one is true. That was not. C, mixing sulfuric acid and water. Right. When you put sulfuric acid, pure sulfuric acid plus water, and you get the solution, aqueous. That process is always exothermic. This is true for strong acids and strong bases, or pure acids and pure bases. When you put them in water, they get hot. Right? That's why we say do as you ought to add acid to water. Right? Because if you add water to acid, strong acid, then the heat that's generated will be enough to vaporize the water, and it'll come splattering back in your face. So we put a little bit of acid in a lot of water to absorb that extra heat. And D, the freezing of water. So water, liquid, going to water, solid, is an exothermic process. Right? It's becoming more ordered. It's becoming lower energy state. Right? So the energy's got to go somewhere. It goes out. It's exothermic. And you may see that today. I think I explained that last Tuesday. Right? You get that. You think you're down to the lowest temperature, and then all of a sudden it goes like that and back down. That latent heat of fusion is an expression of this process right here. Once you get down to right at the melting point, then once those liquid molecules start to organize, they got to give up a bunch of energy, that heat of fusion. And that's when the temperature sometimes bumps up and then comes back down. Okay, so we found our answer. Easy answer. Now, number 4, I think, is next. Which statement about hydrogen bonding is true? Okay, hydrogen bonding. So what's required for hydrogen bonding? Well, any part of the molecule is okay over here, but here you need an electronegative atom, which is usually oxygen, fluorine, or nitrogen. And that's covalently bonded to a hydrogen. So what happens when you do that? Well, the dipole on this region of the molecule, doesn't matter how big that is, the region of the molecule here is a dipole toward that electronegative atom. And that makes you slightly positive here, slightly negative there. So when that happens, you have the opportunity to form an intermolecular bond between this molecule and its neighbor. Okay, so with that in mind, let's see which one of these is true. Hydrogen bonding is the intermolecular attractive force between two hydrogen atoms. Well, no, if we use this example, right, or we want X here and H here plus. So we form a bond between the X and the H on a neighboring molecule. Right? It's not between the two hydrogens. It's between the electronegative atom and hydrogen. So A is false. How about B? The hydrogen bonding capabilities of the water molecules cause, that's butane, 4 carbons, to be more soluble in water than CH3OH. No, butane can't hydrogen bond, right? It doesn't have, hydrogen is not bonded to one of these, it's bonded to all carbons, right? So butane can't hydrogen bond, it's impossible. That's the stuff that's in butane lighters, by the way. Hydrogen bonding of solvent molecules with a solute will not affect the solubility of the solute. That's just wrong. Right? The rule of thumb is what? Like dissolves like. And hydrogen bonding is one of those possibilities. Polar molecules, especially those that have available hydrogen bonding, are going to be more likely to form intermolecular bonds, solute to solvent, if they both have that ability. Or if one of them is ionic and the solvent is hydrogen bonding, like water and sodium chloride, that will increase solubility. But if you don't have polarity or hydrogen bonding available, you're not likely to get a solution formed. Right? So C is false. Hydrogen bonding, D. Hydrogen bonding interactions between molecules are stronger than the covalent bonds within the molecules. Why is that one false?
The strongest, right?
Yeah, the bonds that hold the molecule together have to be stronger. If they're not, then the intermolecular forces acting on the molecule would just rip it apart. So as a practical matter, that has to be false. Otherwise, right, the universe won't work. So that leaves E, which is probably true. Let's see what it says. Hydrogen bonding arises from the dipole moment created by the unequal sharing of electrons within certain covalent bonds within a molecule. Yeah. And the certain covalent bonds are between one of these atoms and hydrogen. Why those? Because the rest of them, the electronegativity is not strong enough to create that strength of a dipole. It's a practical determination. Okay, that was 4. I think 5 is waiting in the wings. Just have to scroll to it. Here we go. Which of the following favors the solubility of an ionic solid in a liquid solid? Solubility of an ionic solid in a liquid solid. Let's see. Solid plus a liquid solvent. Right, so here's our solvent. Here's our solute. What favors this? Right? And I'll subscript it with L because we're not saying what it is. Oh, except this is ionic. All right. What favors the solubility there? The ability to form strong intermolecular forces, obviously. But there are other factors, right? Our 3-step process, right? 1, 2, and 3. Right? We need to break solute bonds. We need to break solvent bonds, often called make a hole. And then we need to form 1, 2, 3. And then these come together and we need to form solute solvent bonds. Okay, so a large magnitude of the solvation energy of the ions. Large magnitude of the solvation energy. So what's the solvation energy? The solvation energy is the amount of heat given up when this process takes place. This is large. Then we're likely to form bond between these two, solvent and solute. Okay, so that's if that's present, a solubility is favored. A small magnitude of the lattice energy of the solute. So what's the lattice energy? Have we covered that? Yeah, I think we covered that. Lattice energy is going from a gas to the solid, right? The free ions in the gaseous state become a solid, right? That energy, if that's a small magnitude of the lattice energy of the solute, we want to go the other direction because this is now a solid, right? So we don't want to put a lot of energy into it to get them apart, right? So that would favor it. So A favors, B favors, what's C? A large polarity of the solvent. Yes, if the solvent is very polar, then it interacts with the ions here. And that's actually another way of saying this one. This one right here. Large magnitude of solvation energy is due to that high polarity of the solvent and the ions. Okay. All of the above, right? They're all true. They favor the formation of a solution with an ionic solid and a polar solvent. Or a liquid solvent. They don't say polar, but A, B, C, and D tell us that the solvent would be polar. All right, that was fine. How are we doing on time? Yeah, it's chipping away. Okay, number 6. I think this one's going to take some work, isn't it? Solid KF has a lattice energy of minus 804 kilojoules per mole. KF, solid, has a lattice energy of minus 804 kilojoules per mole. So the lattice energy actually would be written like this. Right? And that would give us minus 804 kilojoules per mole. Right? That's exothermic. Going from a gas to a solid, it gives up that much energy. Okay. And it has a heat of solution in water of minus 15 kilojoules per mole. So the heat of solution for this KF solid plus water yields KF aqueous solution. Minus 15 kilojoules per mole. Minus 15 kilojoules per mole. Okay. Rubidium fluoride. Now, potassium and rubidium are in the same group. Okay. So we don't have to worry about the influence of fluorine or the fluoride ion. They're both bound to fluoride. So the rubidium lattice energy is what? Minus 768. I think I'm going to run out of board. This is a big problem. And its heat of solution is minus 24. So rubidium fluoride solid plus water. Idiom, aqueous. This is minus 24 kilojoules per mole. Which salt forms stronger attractions with water? Okay, if we look at this in terms of that three-step process, right, where we had, let me try to squeeze it in over here because I think I'm going to need that room. So we had our 1, 2 come together to 3. What we're trying to say about these two compounds is which one has a stronger attraction to water, which one has a larger number 3, right? Or which one gives up more energy when it does that. Okay, so if we do that in terms of a calculation, then the heat for either one of these, the heat of 1 plus the heat of 2 plus the heat of 3 equals the heat of solution, right? How much energy does it take to break it apart, the solute apart, make a hole in the solvent, and then get that energy back? That's the sum of those is the heat of solution. So which one is talking about the stronger attraction? Well, this one. That was the stronger attraction. What is this one going to be? This one's going to be the lattice energy. That's how much energy it takes to break them apart. But it's going to be a positive value. This delta H has to be positive because we got to put energy in, right? So for this one, it's going to be 804. For this one's going to be 768. This one is splitting the solvent apart. Well, it's the same for both of them. The same energy goes into splitting them apart for either one. Doesn't matter. So we actually, all we need to do is compare that together. Right? Okay, if we get this value and compare the two, then we're actually comparing this part of it because this is the same for both of them. All right, so what values do we have here? Well, let's see. For this one, let's see. Let's put the formula over here. Delta H1, delta H2 plus delta H3. So that's going to be a value. This is going to be a value. All right, so this value is the one energy required to break them apart, 804. And this is going to be a plus, 804 kilojoules per mole. Right? And since we're talking about KF and RBF, there's only one K and one F, one rubidium and one F, then we don't have to concern ourselves with mole because we can speak of them. We can balance them because it's going to be the same moles of each. It's not like we have calcium fluoride where you have 2 fluorines and trying to compare to this one. That would complicate things. Okay, and this one's going to be plus 768 kilojoules. All right. How about this value over here? Well, we don't know that one yet, but we do know this one, the heat of solution that was given to us right here. Right. So the heat of solution, I should put another one out here. Heat of solution is, for this one, is actually going to be the amount of energy. These are exothermic processes. We don't have to change the value of this one because it is, in fact, an expression of these two values right here. Oh, no, all 3 of them, excuse me, all 3 of them. So this one is going to be a minus 15. And this one's going to be a minus 24 kilojoules. I'm just going to leave off moles because it's going to be 1 mole for each one. And this is the unknown. Here, here. We compare those two. Right? So this one plus this one is equal to that one for each one. So what does that mean? That means for this one, it's minus 15 and a minus 804. Minus 15 minus 804 equals what? And minus 819 kilojoules. Right? And that's equal to this one right here. Those two. And that's essentially a discussion of that value. I mean, it's not really, because this one does have a value, but when we compare the two, this one would be minus 24 and the minus 768, which is what? 287 minus 782. No. All right. Let's try that again. 8 and 4 is 12. Carry the 1. 7, 9. There we go. Minus 792 kilojoules. So we're comparing this one and this one. Okay. So which one gives up the most energy in this process? That one, KF. That means it has a stronger attraction. KF has a stronger attraction for water than does RBF. And which one would that be? C, KF, since it has a more negative heat of hydration. Okay, so this one is identified as heat hydration. There we go. Okay. You know, that's not right. Yeah, it is. It is. That's right. H2 and H3 both together are heat of hydration. Did I lose anybody? Okay. All right, let's see. We're going to number 7 next. Okay. We got to get the question and then we'll go down to the answers. You know what? I think that one's out of place. That one wasn't easy. All right, 7. All right, what does 7 want us to do? Use the following drawing of a gaseous solute in equilibrium with a solution to help answer the question below. Which of the following statements are true when the piston is pushed in downwards? So we've got this thing here with a piston on it. We got a liquid here. All right, this is our solvent. And we got gaseous molecules up here. And these are going to be the solute. And some of them are going to be down here. So what we're doing is we're applying a force to that piston. Okay, now let's see. Which one of these statements is or are true? Well, statements are true. Should be is true, because there are no 2 of the above or 3 of the above or none of the above. Okay, how about A? This will cause the pressure of the gas to increase and the concentration of the dissolved gas to go down. How about that one? False. Which law are we talking about here? No idea.
Boyle's law.
Huh?
Boyle's law.
Oh, no. No, this is a new law. Right? This is a new law beyond gases, pure gases. This is Henry's law. Henry's law, which states the concentration of the gas in solution is proportional to Right, there's our proportionality constant, proportional to the pressure.
Boils is inverse. Right.
Yeah, and Boyle's is not a mixture of a liquid and a gas. Right, Boyle's is just gas. All right, so A is false. This will cause the pressure of the gas to decrease and the concentration of dissolved gas to go down. The pressure will not decrease, the pressure will go up. Right, initially, and actually it'll go up, and it might initially go up, but then what does Le Chatelier say? We're disturbing an equilibrium situation, so it's going to respond in such a way as to relieve that pressure. So it relieves the pressure by putting some of those molecules into solution, and that decreases the gas pressure above the liquid. It won't decrease it all the way, but it will mitigate it some. C, this will cause the pressure of the gas to increase and the concentration of the dissolved gas to go up. Yes, indeed, it will. We found our answer. Let me see if I made it, if I marked it right on the, yeah, okay. So that means D and E must be false also. In the interest of time, I'm gonna move ahead. 7, 8. Oh, this statement is based upon the same, I should have left that drawing up there. Because 8 is based upon the same drawing. Which of the following correctly states the relationship between temperature and the solubility of a substance in water? No, it's not based on that drawing. My mistake. The solubility, okay, let's just take them one at a time. The solubility, and it doesn't say what the substance is. Doesn't say whether it's a liquid or a solid. The solubility of the substance in water increases as the temperature rises, especially for gases. False. Solubility of a gas in water decreases as the temperature increases. Why? Well, there's your water. There's a constant pressure here, and the temperature is going to change. Temperature increases. Well, we've got some of this gas up here and some down here. All right, so if we've got an equilibrium situation, then the dissolution is equal to the rate of evaporation of that gas. So if we increase the temperature, what are we doing to the whole system? We're increasing the average kinetic energy of everything in the system. The solvent, the solute gas, we're increasing its kinetic energy. So what happens when these gas molecules get close to the surface? They're heading out. Right? We're decreasing the concentration of the gas in that solution by increasing its kinetic energy for each of the molecules. Right? So that's why gases are less soluble at higher temperature. And that makes A false. The solubility of the substance in water decreases as the temperature rises, especially for ionic solids. For most ionic solids, correctly states the relationship. Okay, so that's false. B. We can take issue with this one. It's true for most solids. Most solids. The solubility increases. Solubility of a substance in water decreases. Oh, no, I'm sorry. That's false. Most of the time. There are some compounds, ionic compounds, that are more soluble at lower temperature. Most of them are soluble at increased temperature. But as an absolute statement, that one's false. The solubility of a substance in water with temperature cannot be accurately predicted, especially for ionic solids. That is true. We don't have a theory that adequately predicts solubility. Solubility of a substance in water decreases as the temperature lowers, especially for gases. No, that was false also. Okay. And E has to be false also because A and D are both false. They're not correct. Okay, so C is the answer to this one. Let's see here. You guys are probably ready to go in the lab. This is burn your brain cells. N. A solution contains 1 mole of liquid A and 3 moles of liquid B. Okay, A, 1 mole, and B is 3 moles. Okay. This solution has a vapor pressure of 314 torr. So the total vapor pressure total is equal to 314 torr, correct? At 25 degrees. And then at 25 degrees, something else. Okay, so the temperature is not changing. We don't have to worry about the temperature. At 25 degrees, A has a vapor pressure of 265 torr. 265 torr when it's pure. And B, 355 torr when it's pure. Okay, which of the following is true? Let's see what type of answers we got here. This solution exhibits positive deviation of Raoult's law, negative deviation, solution is ideal. Okay, so what we have to do is say, all right, if the vapor pressure that we calculate for this mixture based upon their pure vapor pressures is equal to this value, then it's ideal. If it's higher, then there's a positive deviation. If it's lower, it's negative deviation. So we have to calculate the vapor pressure, the expected vapor pressure of A and B. So how do we do that? The total pressure is equal to the mole fraction of A times 265 torr. That's the pressure that's due to A based upon its relative amount of the whole. And then the mole fraction of B times its value, 355. So what's the mole fraction of A? Well, what's the total moles? 4, right? It's 1/4. So mole fraction is 0.25. That means the mole fraction of B has to be 0.75. Right? Because mole fractions have to add up to 1. All right, so I'm not going to try to do that one again. 265 times 0.25 is 66,662. Oops. All right, 66.3 torr. And 0.75 times 355 is 266.3 torr. Let's add those two together. And I get rounded off 333 torr. It would be the ideal, right? The vapor pressure, it's measured, the total vapor pressure of this mixture is 314. That's a negative deviation, isn't it? Okay. So the negative deviation is B. It's a negative deviation from Raoult's law. Now, it's not part of the question, the answer, but why is that? Why does that happen? Why would it be a negative deviation? Why would the mixture have a lower vapor pressure? because these two attract one another more strongly than each attracts their own kin. A attracts A with a certain intermolecular force, gives you this value. B attracts with a certain intermolecular force, gives you this value. But when you mix them together, the A and B attract each other more strongly than they attract their individuals A's or B's, which reduces their vapor pressure. And that's what you get over here for the true value of mixture. This is theoretical, this is true. Okay, that's why it's a negative deviation. Okay. Circular nods, okay, that's fine. That was 10. We're still easy, aren't we? Okay, 12, a cucumber. Okay, a cucumber is placed in a concentrated salt solution. Cucumber. Gotta have some seeds in it. There's our cucumber. And we place it in, let's just say sodium chloride concentrated. Okay. What will most likely happen? What are we talking about here? We're talking about a semi-permeable membrane in the cells of that cucumber. Right? So we compare the concentration, the osmotic pressure inside the cell versus outside the cell. Right? You have actually, the way to think of this is what's the concentration of water? Because water is the substance that's going to be moving right across the semi-permeable membrane. So which way is the water going to move? This way or that way? Well, the concentration of water out here is lower than it is inside the cells. So water is going to move out.
Where's the salt?
Mm-hmm.
Where's the salt?
Yeah, towards the salt solution, correct. It's going to, the cells, individually, the cells are going to crenate. They're going to crinkle. And the volume and the mass of the cucumber itself can be measured. It will decrease because it's losing water. So which one is that? Water will flow from the cucumber to the solution. A is the answer. That was 12. And that solution outside the cells, outside the cucumber, is called what? Hypertonic.
Oh, yeah.
13. Already there. Osmotic pressure depends on all but which of the following. All right, what's the formula? Let's see. I think it's in here. Osmotic pressure. Is it not clear? You skipping it? No, it's not there. That's not good. That formula should be there. Look over here. No, it's not there. I'll scratch my head and see if I can remember what it is. Osmotic pressure is, the symbol is pi. And that's related to the molarity of the solution, the gas constant, what else? Temperature. Yep. Because this is in what units? Well, this is moles per liter. This one is in K. And this one is in liter atmospheres per mole K. Right? So the K's cancel, Moles cancel, liters cancel, equals with atmospheres. Okay, we're good. Just had to check myself. Okay, so if that's the formula, osmotic pressure depends on all but which of the following? Atmospheric pressure. Is there atmospheric pressure in there anywhere? No, there's no pressure term in here. Right, so that's it. Atmospheric pressure does not have an influence at all on osmotic pressure. Molarity, yes. Temperature, yes. Ratio of moles of solute to solution volume, that's the same as this one. Right, and that's a constant, so it will be proportionality. Okay, so we found our answer is A. Let's see. Let's just test your memory. Right, shaving cream is an example of which colloid? What's a colloid? It's kind of like a solution, but it's not. It's a mixture. But it's not a solution. In other words, the thing that we would call a solute and would call a solvent don't go through the 1, 2, 3 steps to form a solution. What we're basing the colloid stability on, and it is stable over a period of time. Once you mix these things together, the dispersing medium and the dispersed medium is what we call them. Once you mix them together, then they will stay that way indefinitely, just like a solution would. But it's based upon particle size and actually particle mass. And the reason for that is in a colloid, you've got the dispersing medium, right? These molecules here, and they're zipping around at the speed of sound or better. And what are they doing? They're banging into these dispersed molecules with such force that they keep them suspended indefinitely. If the particles were smaller beyond a certain size, then they'd start to settle because there wouldn't be enough energy in there. So that being said, if we wanted to drop out some of that dispersed medium, we just chill it, right? Reduce the kinetic energy, and some of it would drop out. Unless we chill it fast enough, like Jello. Right? You chill it fast enough and it doesn't have time to precipitate. Okay, so shaving cream is what kind? Well, shaving cream is a liquid. That's the dispersing medium. What's the dispersed medium? A gas. The gas is dispersed in a liquid. And that's called a foam. How about an aerosol? What's an aerosol? Dispersing medium in an aerosol is a gas. And the dispersed medium can either be a solid or a liquid. Smog is an aerosol. Let's see, foam, emulsion. Emulsion is a liquid in a liquid. Right? And we get emulsions, right? We buy one, if you're a milk drinker, you get one of those every time you buy a jug of milk. Right? How do we get the particles small enough? Milk. What are the particles that are dispersed? Fat. The fat particles are dispersed in the liquid medium. And we get them small enough by homogenizing, right? At one time, we just had to mix it really fast and hard to break up the particles. Now, we take that milk and we drive it under high pressure through a sieve with very small holes, and it breaks the fats into very small particles. So they won't clump together and actually rise to the top. A sol is a gas in a solid. Right? You ever seen those ceramic bricks. I showed you the demonstration. You take a blowtorch and you heat it up to where it's glowing. And then this guy comes along with bare hands and grabs it by its corners and picks it up. It's a solid. It's the solid matrix and the gas is suspended in it. And the reason he can do that is because it might glow, the temperature might be high, but there's not much heat there. So those ceramic bricks are the kind that were used on the space shuttle and the kinds that are also being added to the Starship, Elon Musk's Starship. Those black tiles on the outside, those are a solid. Coagulate. Coagulate is not a colloid. Coagulate is what happens to some colloid. For instance, if you have proteins suspended in a liquid medium and you want to bring them out, then all you have to do is change their three-dimensional shape, make them, right, change it, heat them, add salt and salt them out, or you can add acid and salt and change their conformation, and then they'll clump together in larger pieces and drop out. That's what happens to milk when the protein, when the milk goes sour. Bacteria make it acid, proteins coagulate and drops out. It gets kind of lumpy. Remember that movie, what was it called? Alien Nation with Mandy Patinkin? You ought to see it, it's funny. These aliens were stranded in a spaceship. They were slave labor, actually, that were created by some other race, and they escaped in the spaceship and they came to Earth. And Earth welcomed them. Right? And they settled on Earth, and they had various advantages. Right? They had 2 hearts, for instance. They could work in toxic environments, so the chemical industry loved them. They could go into certain areas with no respirators. But one thing that where they were different than humans was humans get drunk on alcohol, right? They get drunk on sour milk. So Mandy Patinkin and James Caan was the human cop that he was paired with. He was a policeman too. And they were sitting around at James Caan's house, and they were talking, bemoaning their various lifestyles. And Mandy goes to the refrigerator and he finds a jug of milk, and James Caan is a new bachelor, so he doesn't take care of himself, and his milk sours in the fridge, and he shakes it. Oh, he hears it slopping around. He says, you want this? No. So he drinks the stuff and gets drunk on it. I just wasted 5 minutes, didn't I? Some of these old movies, you ought to go back and check them out when you have time, of course. Moderate. Now we're into moderates. Okay. Now we're going to look at this one. Yeah, I shouldn't have done that. Fortunately, this lab is not very involved. Okay, a 0.2 molar solution of a solute X in benzene. Let's see, number 3. A 0.2 molar solution of X in benzene. So benzene is the solid. Displays an osmotic pressure given by the formula. So pi equals, and this is the Van Hoff correction factor, right? Times R. Okay, so what we're saying here is this one is a combination of the molarity and that correction factor. Okay, just so we're clear, because it doesn't have M anywhere, so this has to be a combination of the two. So if this is the molarity, right, and that's 0.1, 0.1 equals I times 0.2 is the molarity, And what would I have to be? I would have to be 0.1 divided by 0.2, right? 0.5, 0.5. Right. Before, when we used, why would we use that I value anyway? During our PowerPoint discussions, we used I as whole numbers, right? For sucrose in water, it'd be 1 because it doesn't dissociate. But sodium chloride would be 2, right? Sodium chloride goes into solution and it breaks into sodium chloride ions. So you have double the molarity of your particles. But this works the other direction. 0.5 implies what? It implies that when this X goes into solution, it forms this in solution. One X bonds with another X. It reduces the I rather than increases it. Everybody see that? Oh. So, B, X exists in benzene as X2. When it goes into benzene, the X is associated with one another. We sort of implied something like that would happen when we discussed ion pairing. Sodium chloride would be 2, would be I equals 2 in dilute solutions. But if the concentration increases, there's more probability that sodium and chloride would find each other and bond temporarily. And that would decrease your 2 from maybe to 1.8 or 1.7. So that's the same type of thing that's happening here, only this is a purely hypothetical. Okay. All right. How about 4? Let's see. Let me scroll that up down. I think there's an E down there. Yep. Which of these solutions, 0.1 molal sodium chloride, 0.15 molal glucose, 0.1 molal calcium chloride would have the highest vapor pressure, the lowest boiling point? Okay, so we got 0.1 sodium chloride, 0.1 molal sodium chloride, and 0.15 molal glucose, right? And 0.1 molal calcium chloride, right? We assume these are aqueous solutions. All right, so 1 is vapor pressure, and 2 is boiling point. Okay. So, what is vapor pressure dependent upon? Well, the vapor pressure of the solution is equal to the mole fraction of the solvent times its pure vapor pressure. Right? So, this would give you a certain vapor pressure. This is a higher concentration of the solute, which decreases the concentration of the mole fraction, decreases the mole fraction of the solvent. Right? So between these two, the vapor pressure here would be higher. No, excuse me. This is 0.2 molal ions. That's what we're focused on, right? Because it breaks into 2. So this one would have a higher vapor pressure than that one. How about this one? Well, this one breaks into 3 molal ions. So that's what we're comparing. The higher vapor pressure is the one that has the lowest concentration of the non-volatile solute. So it would be C2, this one right here. This one. That one would be the highest vapor pressure. Yes, highest vapor pressure would be glucose. How about the boiling point? The boiling point would be elevated for the higher solute concentration. Right. That's based upon here, molality, and then K. So as the molality increases, the boiling point would increase, the change in temperature. All right, so which one's highest? This one right here, 3 molal. So it'd be glucose, calcium chloride. Wait a minute. Did I put those up here right? Oh, lowest boiling point. I'm sorry. That's the highest boiling point. Lowest boiling point, yeah. This is 0.2, 0.3, 0.15. Yeah, okay. Did I confuse you again? Sorry. We want lowest here, and highest here. Right. So in that case, glucose would be for both of them. Now let me see. Is subsequent? Yeah, we're going to need the same thing for this one. For 5, do we have the same situation? 0.1 molar, 0.15 molal, excuse me, 0.1 molal. Yes. Okay. So in this case, we're looking for the lowest vapor pressure. Lowest vapor pressure and lowest boiling point. So the lowest boiling point is still going to be glucose. But how about the vapor pressure? The lowest vapor pressure is the one that has the highest solute concentration, which means the lowest mole fraction of solvent.
Calcium chloride.
Calcium chloride, yeah. There you go. So that would be C. And let me check to be sure I don't need it again. No, we're into difficulties now. All right. Yeah, I got 6 minutes, nominally speaking. Oh. Oops. Dyslexic today. Everybody. And this is number 2 of the difficulties. You scroll just a little more, don't I? There we go. A solution is prepared from 53.8 grams of a non-volatile, non-dissociating solute and 85 grams of water. So we have 53.8 grams of the solute and 85.0 grams of water. Solution formed from that mixture. The vapor pressure of the solution at 60 degrees is 132 torr. So the vapor pressure of this mixture is 132 torr at 60 degrees. Okay. The vapor pressure of water at 60 degrees is 150 torr. So this is the solution. And this is water. Is what? 150 torr. At the same temperature. Okay. What's the molar mass of the solute? Okay. What do we need to calculate molar mass? Mass per unit mole, right? So we got the mass. Yeah, we got the mass right here. What we need is the number of moles. Okay. So how do we get the number of moles out of this? We're talking about vapor pressure, right? We're not talking about boiling point. So we can't say anything about the boiling point. So I think what we're into now is Rayleigh's law. Right? So the actual vapor pressure of the solution is equal to the mole fraction of the solvent times the pure vapor pressure. Solvent's water. Okay, so this value is the pure, right, 150. And this value is 132, right? 132. So what's the mole fraction? The mole fraction is 132 divided by 150, correct? So mole fraction of water that should be water is equal to 132 divided by 150, which is 0.88. Right? That's a dimensionless number. It's a fraction. All right. So if that's the fraction of the solvent, what's the fraction of the solute? Well, the mole fraction of the solute equals 0.12. That's the mole fraction of the solute. All right. So this mole fraction, we got to get the moles of the solute. That's the mole fraction. It's that many moles per total moles. So what's the total moles? What we have to do here is assume that the moles of this solute contribute very little to the overall moles. So we know the moles of this one, right? We just divide by, what's what, 18.02, isn't it? 18.02 grams per mole. Right, so the moles of water would be 85 divided by 18.02 is 4.717. 4.717 moles of water. Oh, okay. So this is equal to an unknown number of moles. Right. We may not need this one. Actually, yeah, let's use this one. So 0.12 is equal to the mole fraction of X, which is X moles divided by X plus 4. Is everybody keeping up with me? 4.717 moles. Okay, we're using a little algebra. We've got a solution, a problem in one unknown. Now all I have to do is solve for the X, and that'll tell us how many moles of our solute we have. Okay, so 0.12. Let's see, bring it over on this side. So here we're going here. So this and that times this, first of all, is 0.12x plus 0.12 times 4.717. And that's equal to 0.566. And that's equal to X. Okay. So now we get X on that side. Becomes a negative over here, right? So it's 1 minus 0.12. 88. So 0.566 equals 0.88x. Don't lose anybody there. Right. 1x minus 0.12x is actually that value. Okay. So now x is equal to 0.566 divided by 0.88. And that's 0.643 moles. So now we've got mass 53.8 grams and the moles at 0.643 moles. So we'll divide that into 53.8. And that's 83.6 grams per mole. E. Okay. Those two. And I'm out of time. Let me see how many more I got left to do. If there's a lot, we'll just go in the lab and I'll finish it up later. But if there's just a couple, we can get into that. I think there's, go back to my original here.
This is the last one.
11. Yes, yeah, okay, so we'll finish this one. There we go. You have a 10.4 gram mixture of table sugar and table salt. When this mixture is dissolved in 150 grams of water, the freezing point is found to be minus 2.24. Calculate the percent by mass of sugar in the original mixture. Okay, this one's going to take some doing. Okay, let's get everything up here that we know. 10.4 gram mixture. So total mass equals 10.4 grams of sugar and table salt. That's sucrose and sodium chloride. Okay. When we put that in 150 grams of water, right? So the mass of the water or the solvent is equal to 150 grams. Right? We know we're going to have to calculate molality, so let's just make it kilograms. 0.150 kilograms. That's the solvent. And the delta T, change in temperature of this solution, is minus 2.24. 2.24 degrees C. And I'm only interested in the absolute value. Yeah. I don't need the minus sign to do the calculation. Right? Right, freezing point depression. I just need to know how many degrees it moved. That's why I put those two lines there. And that's equal to what? Well, we need the freezing point depression constant for water, and we need the molality of the solution, and we need the correction factor. We know we're going to have a correction factor because of that one right there. Okay. All right. So if we're going to calculate percent by mass of sugar, so we're looking for percent mass of sucrose. That's what we're looking for. In order to calculate that, we need the total mass. We got it right here. We need the mass of the sugar somehow. Right? But we got a mixture here. All right. So what we can do is we can separate this into two factors. We have an I for the change in temperature is going to be due to the I for the sucrose, which would be the same for both, times the molality of the sucrose. And then the effect of sodium chloride will be this term. Okay. I think that's the trick to the whole problem, recognizing that this is a summation of those two effects. Right? Beyond that, then it should be fairly easy to work through it, as long as you're comfortable with algebra. So if we're going to need to know the mass of sucrose, right? Percentage mass of sugar in the original mixture. Mass of sucrose, so let's let it equal to X. So X equals the mass of sucrose. That means that the mass of sodium chloride is 10.4 minus X. Is the mass of sodium chloride. All right. Oh, we do have a formula for sucrose because we've got to convert these to moles in order to get molality. Right? All right, so what would be the moles here? Well, it'd be X grams divided by grams per mole, right? Grams per mole of sucrose. So sucrose is C12 H22. No. Yeah, H22 and then O11. So the molar mass there, I need a calculator for this one. Carbon, 12.01. So it's, let's do it over here. 12.01 times 12, and then 1.01 times 22 for hydrogen, and oxygen, 16 times 11. They would add them together. And 1.01 times, and that one, 16 times, and that one. So this is 342.34 grams per mole. All right. So that's the mass of sucrose. The moles of sucrose is equal to X divided by 342.34. And the moles of sodium chloride are equal to 10.4 minus X divided by, see, sodium is 23, right? Yeah, 23. And then 35.45 for chlorine is 58.45. And that's, this is moles. This is moles. Okay. All right, so what's the molality of sucrose? It's this one, moles per kilogram. So the molality of sucrose, let me erase this. Molality of sucrose, let's see, this is mass. Mass, there we go. The molality of sucrose is equal to the moles of sucrose, which is X divided by 342.34 divided by the kilograms of salt, 0.150 kilograms, mole kilogram. Okay. The molality of sodium chloride is equal to 10.4 minus X divided by 58.45. That's also divided by 0.150 kilograms. Okay. What's the K for water? We looked it up once before. Here it is. It's in the useful information. 1.86 degrees C kilogram per mole, or degrees C per molal. 1.86. This is 1.86. There we go. This value is 1 because sucrose does not dissociate. This value is 2 because sodium chloride does dissociate. Okay. So this value here is equal to this one plus that one. We know this value, we know this value, we know that value, we know that value. If we substitute in here molality for this one, molality for that one, we have an equation in one unknown, X. Okay. So let me see if I can get that on the board. 2.24 equals. That's 1. So we really only need 1.86 here. And then we need this expression for sucrose. X divided by 340. Let's simplify this one before we do that. All right. This is in the denominator of the numerator, so it's in the denominator. So it's actually this times that. Correct? And let's see, switch those around and multiply it by 0.15. All right. So this now is, I'm going to put that over here. X divided by 51.35. Okay. Then plus, this is 2 times 1.86. And this factor, can it be reduced further? Yeah. 5845 times 0.15. And that is 10.4 minus X over 8.768. Okay. So there's our equation, the one unknown. We just have to solve for X. Yeah, might as well get with it. Okay, 1.86 divided by 51.35. Is 2.24 equals. This one divided into that one is 3.62. 2 times 10 to the minus 2 X. And then this one is 2 times that one divided by this one. And that's 4.243 times 10 to the minus 1 times 10.4 minus X. Right, so this one can be reduced further. 10.4 times that one is 4.412 minus 4.243 times 10 to the minus 1 X. And this is 3.622 times 10 to the minus 2 X. Okay. And this is all equal to 2.24. So if we leave the X's on this side, put them together, bring this one over here, that makes it a minus. Yeah, that's okay. So 2.24 minus 4.412. Is minus 2.172 equals, and then we add these two together. Well, that's a negative and this is a positive. So I got, let me see if I can ratchet it down. There we go. And then I'm going to subtract this one from that and give us a negative number, I'm sure, because 10 to the minus 2 and 10 to the minus 1, this one's bigger. This is a minus 3.88 times 10 to the minus 1 X. Okay. Don't forget the x. Now, x is equal to this one divided by that one. A negative divided by a negative is positive. So let's see. I'll do this 2.172. Okay, so x is equal to 5.597 grams.
Correct. X was the mass of the sucrose.
So there's the mass of the sucrose. And we want percent. So percent of x equals 5.597 divided by 10.4 times 100. Is 53.8% sucrose. Close, 53.9. Rounding error somewhere. Can you do that? No. Okay. What if I make an extra credit? Then if you have time, you can do it. There are two tricks to this problem. One is recognizing this relationship here, these two. And the other is algebra. Which one do you make your unknown? You want to make your unknown a value that when you solve for it, that's the answer. That's closest to the answer you want to get. Okay. That's it. Time for a lab.